Welcome to solverfy.
Okay, in this problem we have an atom that's in an excited state 3.5 eV above its ground state, which lasts on average for 2 microseconds. We're asked to find what wavelength photon would be emitted once this atom drops back down to its ground state, or consequently, what photon wavelength, what energy photon would be required to boost it to this energy state. We're also then asked for the uncertainty in its energy, given our delta t. The equations we'll be using, we need the relationship between the energy of a photon to its wavelength, and we will need the uncertainty principle in terms of delta E and delta t. We will be using the Planck constant, reduced Planck constant, and speed of light. So let's jump into it. It should be a relatively straightforward problem. So for the photon, using the relationship E equals hc over lambda, we can solve for lambda, and we will use the energy of our energy level above the ground state. This change in energy will correspond to a photon of that same energy with its wavelength. So plugging in some numbers, we would have 3.55 times 10 to the negative 7 meters. So about 355 nanometers for the photon. Now for the uncertainty in energy, we can use the uncertainty principle, delta t greater than or equal to h bar. We know delta t, so we can find delta E straightforwardly as h bar over delta t, which will come out to be 5.27 times 10 to the negative 29. Very, very small. Just for perspective, in electron volts, this would be 3.3 times 10 to the negative 10 electron volts. So this is many, many orders of magnitude smaller than the actual magnitude of the energy level itself. And those are the main results. Pretty straightforward problem.